Good morning, everyone. Welcome, and thank you for taking the time out to come and listen to what a small engineering company from rural Oxfordshire in the UK has got to say. So I've been listening with quite fascination to some of the talks we've had so far over this conference. A lot about systems, a lot about technology, and we touched on last night about people. But one of the things I want to talk about is innovation. And what sits behind every great technology and great system is an innovation. How do you get that innovation, and how do you get the most performance out of that? So I'm going to talk about technology, innovation, energy efficiency, which might be a little bit of a surprise knowing that we're a racing team, and also the data that sits behind and unlocks the potential in everything we have. But before I kick off, how many of you came to the talk about NASCAR on Monday evening? So if you want the total summary of my talk, we can turn left and right. But before I dive into some technical detail, what I want to talk about is a little bit about Williams, a little bit set the scene, as I said, why a small company that's probably known most famously for our racing cars is doing here today. So ever since man made any sort of transportation, whether it be a horse, a chariot, a boat, a plane, a car, they always wanted to see how fast it went. It was always a competition. We always wanted to win and have the fastest whatever it was. Williams was established 35 years ago by Sir Frank Williams, and his sole ambition was to win Formula One World Championships. That's what made him get up in the morning and probably made him never go to bed either. However, we're a lot more than that. We are the only listed Formula One team. We're listed on the Frankfurt Exchange. And we're a Formula One race team. That's our core. We always have been. But we have a very big and growing advanced technology business. Over the years, we've won 9 Constructors' Championships, 7 Drivers' Championships, and are one of the top 3 most famous and successful Formula One teams of all time. However, in 2010, we took a bit more of a brave strategic direction. We decided that what we do has much wider applications outside of purely just going round those racetracks. And we set up Williams Advanced Engineering. So, as I said, what makes us get out of bed in the morning? So, for Sir Frank and the Formula One team, it's quite simple. We want to compete to win. There's no point being in Formula One to come second, third, ninth, 10th, whatever. You want to win. We want to maintain and develop our brand as a luxury brand globally, and more importantly, people. We want to retain and recruit the best industry talent we can find from across all of the engineering, science, and technology sectors. Advanced engineering, however, has a different challenge. We need to develop high-growth business and annuity revenue streams. We need to take the technology to market and pay for our racing. We put all that effort into the technology, and Sir Frank and the management team all believe there is a societal benefit that we should give back by commercializing that technology. And also move away into different sectors. That graphic there is the start of that. That's not actually a product, by the way, just in case anyone was wondering. That shows our transition from motorsport through to high-performance automotive. And then I've got a few things at the end which are probably quite surprising transmissions of F1 technology to other markets. We're very lucky. We have a very understanding bunch of shareholders that see Williams as a long-term business. It's not about growing a dividend this year. It's about generating value for the future. So I'm hopeful everyone knows about Formula One, so I'm not going to talk too much about the actual side, the sort of race car side of it. I'm going to talk a little bit about advanced engineering. What from F1 have we taken and do we think is a core USP to other markets? High-performance, hybrid, and electrical solutions. I've got a case study of that a little bit later on, but it's a key growth market for us. We've seen about the self-driving car and all of these new innovative Google pod cars, etc. They all need power somehow. Is just the normal combustion engine the way forward in the future? Open question. There's lots of other opportunities, and we want to be able to push that forwards. Aerodynamics and thermodynamics. F1's famous for aerodynamics. Lightweight materials, the same thing. We've been using carbon composites since 1985 as a complete monocoque chassis. High-performance dynamics, it's amazing if you combine all of those things together, what you can actually get out of a vehicle that's existing today or any other engineering system. We do make things, very small volumes. I'm slightly conscious I'm in Detroit, the home of the large volume automotive, and we measure anything I consider large volume if I go into hundreds of anything. Who do we do it for? We do it for a variety of people, to a variety of sectors. Your big OEMs. We also sometimes play with fighter jets, aerospace jets, boats, even down to sports sciences. We really want to push out into our markets beyond motorsport, automotive, defence, energy, life science. But I've mentioned the word industry a few times, and before we go on into innovation, what I want to talk about a little bit is about Formula One and also motorsport as an industry, which is actually quite an important industry in the UK. It's a little bit of a complicated slide, but we'll start on the far left. People often ask me, why is F1 different to many other race series, NASCAR, IndyCar, and all of the others? We're the only race series where every car is different, and you'll look at them all and say, well, yeah, they're all painted different colours, but that's not quite the same thing. But the car is fundamentally different. There's a set of regulations, and each team will make their own chassis, own powertrain, own aerodynamic surfaces, and that's really what differentiates Formula One. Its core DNA is innovation. The regulations are guidelines and a framework in which you have to work, but beyond that, the drawing board is completely blank. It's not a case of what did we do last year, but what can we do this year? And that comes at a cost. Formula One teams will spend, on average, between £50 million to over £300 million on competing in Formula One. I quite like the slide on the left there, and that shows the cost that each of our relative competitors spend in terms of Formula One. So Williams is down here. We spend about £105, £110 million a year. Last year, we were P3 in the championship. So up here, we are still in P3, above those parties that sometimes spend up to 3 times what we do. So Formula One, contrary to public belief, is not about throwing money at things. It's about finding innovative solutions to the problems you have. But if we talk about the industry, in the UK, the motorsport industry more generally employs over 41,000 people and has a £9 billion turnover. 70% of all open-wheeled racing cars are designed and built in the UK. A number of the key suppliers for IndyCar are UK companies. And these aren't large conglomerates. It's a very fragmented industry, and they're all often co-located within a region called Motorsport Valley, which is basically just to the west of London in rural Oxfordshire, Buckinghamshire, Northamptonshire, which means that people point is very important. There's no geographic factors to why I can get an engineer off Mercedes or why an engineer that Mercedes can take off me. It's all about your brand, the culture you have in your business, your desire to win, and their perceived career path. It's a very competitive business to get those few engineers that we really will make a difference. Formula One in total employs about 6,000 people out of that 41,000 people. And to give you an idea, around 400 million people will tune in to watch the Austin Grand Prix that's in a week's time. That gives you the scale of the market. But how do we make any money? Racing sounds quite expensive from the chart on the left. So we get a cut of the TV money. Basically, it's divided up amongst the teams. We take sponsorship. The car, of course, like most sports, is covered in sponsor logos. But both of those are really tied to your success. If you're trying to make a long-term business, listed business, I've got my obligations to my shareholders, I need something else. And that's one of the reasons that we have Williams Advanced Engineering. Their commercial work provides a solid underpinning to our group's performance. So that's a little bit about the context of Formula One. I wanted to set that out for you. But now to talk about innovation and how we actually make success. It's all about people. And why do we bother with F1? What's come out of it? It's a common question. Oh, it's all about the technology. Where does it go? So if we start on the left, if you ask our designers what their 3 key principles are, they'll say safety, compliance to regulations, and performance are their 3 rules on which they base all of their design decisions. You'll notice reliability is not on there. Reliability in our world has to be a given. You've got 400 million people tuning in, they want to see a show. We have to remember we are in entertainment. That's not to say you can't have freak engineering failures, they do happen. Touch wood, not to us too much this season. But really those three things, safety is paramount to us. But what technology really has come out of Formula One? I mentioned composite structures earlier. We've been using composite structures since the mid-80s, but it's only in the last few years they've really ended up in the aerospace industry in the form of the 787, and obviously the first composite production car, the BMW i3. So composite structures, how to model those in crash is a particularly important aspect for us, and one that we again base further work outside. And then we've talked a lot about the connected car today and yesterday, and we actually have the challenge of sometimes needing to make our cars more dumb. I think probably we've been leading the way in terms of various systems: traction control, ABS, launch control, active suspension, where the car stays flat through all cornering scenarios. All possibly now more common features on high-performance road cars, or even actually most normal road cars. Most of them have been honed in motorsport. Motorsport rarely is the sort of white coat R&D laboratory. Motorsport is about picking ideas. We go around various sectors hoovering up ideas that we think are interesting. And these are sort of your university level, R&D lab level ideas. And we want to push those forwards and incubate them and turn them into reality. Motorsport is a great test bed. You get feedback on your design every 2 weeks. And it's very public feedback as well. If your part goes wrong at the weekend, you will know about it. You will know about it personally. And when you walk back into the office on a Monday morning, 400 million people have seen your part's gone wrong, and everyone else inside our company knows who drew that part and why and how we're going to sort it. However, we don't have a blame culture. It's all about moving forwards. Safety systems, a key thing. As I said, Formula One likes to take a concept and move it on. Crash tests. It was established quite early on that having a solid steering column in a car was a major cause of injury during front-end collisions, because obviously the column didn't collapse. So they started doing dynamic crash tests on the steering columns, making them crumple, etc. Formula One took that a stage further and started doing full dynamic crash simulations and tests on full vehicles. One of the first people to do that, waste an expensive prototype, slamming it into the wall. For those of you that watch Formula One, you'll have seen last weekend in Russia there was an accident during qualifying. The car hit the wall at 46 G was the recorded impact. The driver was seen waving. He was taken out of the car by the medical team as a precaution and was seen waving and giving the thumbs up. He returned the next day and drove in the race. So I think that's the testament to the level of focus on safety we have and the safety systems that are within the car. Excuse me. And finally, data analysis. The car runs on data, as you might expect. We have restrictions on how much we can capture, and our role on running the car is actually passive. I'll go into how we do the data a little bit later on, but there's been a bit of push that we only receive data. We can't actually go in and action the car live. We used to be able to, and then some drivers complained that we were just replacing them. Might be a little bit easier to deal with on some occasions. But we've talked about what are the drivers, what's the need, but what is the most important thing in Formula One? What's the most important commodity? It's not money, it's not really people either, to be honest. It's time. So to give you an idea, the complete life cycle of our product is 18 months. 18 months from a release of regulations and a blank sheet of paper to the car and all its spare parts being put into a box and put into our museum to be preserved for whatever. So we generally have an 18-month life cycle. We've got about 6 months to design, or 6 to 9 months to design and construct the car. In the months of September and August, we'll have released over 5,000 parts to production, and the new car is being built as we speak, or being manufactured, ready for next season. You always have to look at the season ahead and the next event. We're driven by regulation. They only firm up the regulations in sort of June, July of the previous year, so it compresses that cycle. The regulators also reserve the ability to change the regulations whenever they fancy as well. So sometimes we could have under a week to respond to a change in regs prior to attending a race. In that time, we may have to design, test, and manufacture a replacement part on the car. Do we build on from each year? The cars, depends if you're a Formula One fan or not. Lots of people tell me the cars all look the same. They're really not. And our engineers would definitely argue against that. And we really start from a blank piece of paper each year. And the reason of that is to try and free that innovation. We don't say, can you take what you've done last year and just make it a bit better, please? Because we only make small volumes of things, it's actually more efficient in terms of performance we get out the other end to say, blank piece of paper, up to you, off you go. That means we'll probably release to production over 20,000 components a year, bearing in mind we only employ 700 people. We do run 24/7 like any modern manufacturing plant in order to meet the demand. And our output is 2 cars at 21 races next year around the globe. That is our only output and product for 700 people and 21,000 parts. So the time point, I can never push the time point enough. There is no ability to slip the schedule. You can't delay the release. You can't say, oh, well, going to have some very upset senior management, probably get a little bit of a battering in the press, maybe from our shareholders, but it's all right, we'll go to the next show to unveil the product. I've got 400 million people waiting for the racetrack, and I can't say, would you mind awfully if I moved Austin a couple of weeks later, because that'd be really handy for me. So how does that drive a culture? So, and this is really a business culture. It's honed from racing and design, but it's really about business. So we have 4 pillars, and we try and apply this across the whole organisation. Leadership, key activity. We heard earlier about last night about how a leader could inspire people. So Frank Williams, for those of you who know him, is a tetraplegic. He's been in a wheelchair since 1987 with limited use after a road accident. He's still in work every day. He's around by 7, and he'll still be there at 7 in the evening. He's a real inspiration to the business, but actually what that means actually really means empowerment. It's the level down. We empower our people to understand what they do and to perform it to the best of their ability. And that leads on to that continuous improvement point. Every race, the car is different. Every race, we improve our procedures, our processes. We've been doing this for 35 years. So you would have hoped we kind of got it by now, but there's always a little bit of margin to find. That takes us on to the pit stop. The pit stop is basically a piece of scheduled downtime. 18 guys, and all you have to do is change a wearable part in the car, namely 4 tyres. 18 guys go out into that box, and we measure what's called car time in the air. That's the time the car is stationary. So in that time, they must jack the car, undo 4 nuts, remove 4 wheels, replace 4 wheels, replace 4 nuts, drop the car. On average, that should be 3 seconds in Formula One to coordinate those 18 people. There's no panic, there's no shouting, there's no running around in circles. It's a pre-disciplined process. You would think that those guys are professional pit stop guys. That's their job. Not at all. They're recruited. They are our travelling mechanics. They're recruited because they have trade specialisation in composites, electronics, mechanical systems. Their job is to actually maintain, operate and run the car, and that's what they do on a Sunday afternoon. We practice that continuously, and each one of those seconds really does count in a race scenario. When you look at, we measure performance in thousandths of a second, so anything we can take off a pit stop is key. But what underpins all of that? And that's data. We try and use data to drive decisions. And we actually, if you speak to our technical team, have a slightly different view on the sort of the monitoring and gathering of data. There's been probably a proliferation. I often hear various industries telling me, it's great, we've got all this data, we've got so much data, we've just upgraded this. We don't know what to do with it, but we've got it all. And I visited such a food sector plant, and they were explaining to me how they had this great new reporting system in, and the guy was explaining to me how he did it. What he used to do is every hour he used to go and take a reading off something and mark it on a chart, join it up, and then he put it in the filing cabinet. He said, no, we've had this great multi-million-pound investment in the plant. It's all done automatically. I said, well, what do you do with it? He goes, Well, at 5 o'clock when I go off shift, I print it out and I put it in the filing cabinet. So data analytics, data services cost money. You have to buy the sensors. You have to store the data. You have to do something with it. There's a cost to us, but for us, the cost is actually weight. For every sensor I put on the car, it probably needs a wire, unless it's wireless, whatever. But it needs power. The sensor costs weight. It costs us in weight, and weight translates to lap time. Every gram I can take off the car, we measure the paint, and we change the paint surfaces to try and make sure that we minimise the weight the car has on it. So our engineers always ask a different question: what decisions do I need to make? What data do I need to make those decisions? And once I've established that, how do I go and collect the data? And that's the gating process for which a sensor will find its way onto that car, not the fact we found a great new sensor that would be really cool to use. That does happen a little bit, but gets thrown off pretty quick. But data really is at the underpinning of the whole organisation and the business, and we use it to drive decisions both in a corporate world, our advanced engineering business, and also within Formula One. Sometimes those guys have to make decisions quickly, and they often say they're on the wall, oh, they've decided to come in. They haven't decided anything. We have a number of scenarios and a number of models running in the background, and using that we'll then decide on when to bring the car in for a pit stop. So hopefully that's a little bit on why and how we develop the technology. But the next question is, well, what happens to it next? So to illustrate that, I'm going to talk a little bit about energy storage and about powertrain technology. So I'd say within the last 5 years, energy storage is probably one of the big pushes out of Formula One. For those of you who don't know, Formula One since 2009 has run hybrid engines. Basically, there's been a motor generator unit connected into the engine and a battery to store the energy. So when they set about that regulation, though, Formula One didn't specify any of that. They said, as of 2009, if you would like, you can store energy from the car as it goes around the circuit and reuse it. That was the regulation. That was the entire sentence of the regulation. Off you go. Don't have to do it if you don't want to. So that was the innovation driver. There was an opportunity to get more performance out of the energy we get from the fuel that we put into this vehicle. So we looked at two different routes. We looked at flywheels and we looked at batteries. And we actually progressed and made investments into both of those technologies, had them level pegging, then decided which one to use for Formula One and which one to use for other markets. So what I'm going to do is do a little bit of a case study on each of them. So battery systems. Battery systems were the system we eventually put in the Formula One car. They're still there today. And there's also heat recovery out of the turbo wastegate as well on the newest Formula One cars. So we started with that. We started with Formula One, a kinetic energy recovery system battery. Electric lithium-ion batteries, nothing particularly new, quite common in the automotive sector, your Priuses and other sectors. But what's the difference between their battery and our battery? We like to think we push the envelope of performance in all of the dimensions: packaging, weight, power density, etc. And also the control and management of that to get every last eco power out of it. So we started there, and then we said, well, we've got that. Where to go next? Well, road vehicles was the obvious choice. So the car that you'll see on the bottom of the screen is the Jaguar CX-75 hybrid supercar prototype that Williams Advanced Engineering developed for Jaguar. That has 3 performance criteria: the performance of a Bugatti Veyron, the range of a Chevrolet Volt, the old one, and the emissions of a Toyota Prius, and has to look that shape. We achieved those specifications to 5 fully functional demonstrators to journalists within 18 months. And that speed of a response is something we apply into all of our sectors, based on transferring that core DNA of racing into everything we do. But we didn't stop there. From the CX-75, we then went forwards into Formula E. I don't know how many of you have seen the Formula E all-electric race series that's currently going around the globe. There was one in Long Beach, I think, last year or late this year. And that's really about demonstrating the value and the performance of electric vehicles and trying to push away that stigma of, oh, they're not very fast, they're not very exciting. Something that Tesla has tried to do but this takes it to a whole new racing level. But that's not where we stop. We're looking forwards into aerospace, defence, mass transit and renewable energy as new markets for those battery systems. And for us, it's really about the software, the data and the performance we can get out of existing technology. So that's batteries, which are probably a little bit more common. Flywheels, however, are probably a little bit more different. So this is a little bit hard to visualize just on one slide. It's a mechanical battery. So there is no mechanical link to the transmission here. There is a motor generator unit attached to the transmission, and this is a mechanical battery. Energy flows in electrically, and it's a composite flywheel with magnetically loaded composite, and basically spins in a vacuum at 45,000 RPM. That device is probably about a foot across in diameter. So we actually acquired that technology. We didn't develop it ourselves. We bought it off a small startup that had bought it out of the British nuclear industry. It's the same technology that goes into a nuclear centrifuge, apparently. So we bought that technology, we incubated it, we took it out into other motorsport markets. We took it to Porsche for endurance racing. We took it to Audi. That device has been in the Audi e-tron Quattro for the last 3 years and is their hybrid energy store inside the car. But for us, we were always looking to the future. It was never about racing. Racing was a good way to work out whether it worked or not and get out all of the technical teething issues quickly. The real sweet spot is mass transit. So I didn't know until someone pointed out, but a London big red double-decker bus on an average day has the same energy cycle as the Audi e-tron Quattro going around Le Mans, apparently. And so this device, retrofitted or fitted new, can save up to 30% of fuel on operation, which gives it a payback in a couple of years. Its applications there go bus, tram, truck, and various other markets, as long as they stop and start very frequently. But for Williams, as I said before, we don't manufacture mass items. We like doing technology incubation. We've taken an idea and found an application for it and come up with a product. We then divested it to GKN PLC, some of you who may know from their automotive connections and driveline, and this will be now incorporated into some of their new bus, tram, truck, highway product lines. So these were the more standard technology transfer, but I said at the start I'd talk about a few things that were probably a little bit more unusual. We would do work in defence, and data comes back in here. That is a Scout armoured vehicle for General Dynamics to be sold to the British Army and multiple other armed forces around the world. We are providing the data backbone and the data system that sits inside that, again, taken away from some of the approaches we do in Formula One, plus it's lightweight, high performance, durable. And the one on the right is actually one of my favourites. This is really a complete step away from the world of racing. Have you ever been to a supermarket and you walk down the aisles past all the chilled stuff and you get really cold feet? It's really cold in there. What happens is all of the cold air they're pumping into those cabinets just falls out into the corridors. So we partnered with a small startup that had an idea that said, we think we could catch this, but we've been able to, using F1 aerodynamics, the product's been in our CFD clusters, it's been in our wind tunnel, to test and prove out and improve the performance by taking the F1 approach to aerodynamics into the retail sector, and it's currently on trial with J. Sainsbury, one of the big supermarkets in the UK. So our work doesn't stop in automotive. We like to go through into other sectors. So that's a little bit about where we are today. I suppose the other thing to look at now, as a lot of the things that these presentations have done, is look into the future and where we see our challenges. Commercializing technology from early stage is always a challenge. We're a small company, we're not a giant OEM that can afford to run multiple project streams all at once. And I have a competing time frames as well. I've got guys that want to put the product onto the next vehicle and onto the next racing car and make a success. However, if I want to exploit it, I probably need to protect it in some way, and that brings the whole conflict of, do I patent something, how do I protect it versus exploiting it? If I put a patent in and say, I've effectively told my Formula One competitors what it is, and I'll probably be told I've got an unfair competitive advantage, so they won't allow me to use it. If I don't protect it, I'm going to struggle to commercialize it. So picking the right early stage technology and understanding how that goes forward into the open market on a long-term roadmap is key. And in terms of future direction, where do we find the most interesting areas? Automation, autonomy are top of the list. And that was before I actually knew what, and I wrote this before I saw all of the other speakers' presentations and titles. We do a small amount of work in the autonomous space, and that's becoming even more important. Anything from simulating how an autonomous vehicle works with regard to passengers, how we'd understand the liability, through to the physical design. The video we saw of the little pod car that could go and park in your closet kind of excites us, because that's the sort of broad brush, clean sheet of paper design challenge that someone like a Formula One team likes to embrace and like how we like to work. Big data and integrated vehicles. Everyone has mentioned this without fail so far. A Formula One car spits out about 20 gig of data in a race per car. We transmit all of that back to our base in Grove to look at. But we have both advanced analytics and probably 25 people watching it on a second-by-second basis. Not quite scalable into the mainstream automotive world. But that link between machine, user, and the wider community, its OEM or other, is always going to become more and more important as we go forwards. And finally, energy efficiency. Everything we do at Williams is meant to be get the best performance from the energy we have. Energy efficient performance is the strapline on everything we do. It's not necessarily about increasing the horsepower. It's about getting the most we can from the energy that we put into the system. And that's regardless of what energy source it is, whether it's a fuel cell, whether it's a lithium-ion battery, whether it's a supercapacitor, or whether it's a standard gasoline engine. It's about getting the most benefit out and performance out of that fuel. Where will that come? Powertrain technology, control systems, structures, the work in composites, plastics, light aluminium structures, and the combination of those within a vehicle is actually very exciting for us, and some of the areas that we find could be important going forwards. So thank you very much for that, and hope you found the world of Formula One interesting. And I've got a few minutes left, judging by this clock, so happily take any questions you might have. Anyone? Nope. I think there's a microphone on their way. Oh, I think there's a microphone on its way.
I was just curious, as far as your battery, so whether you have it in the Audi or you have it in the Mercedes for the F1,
What's the difference? So our current battery system, you're very right, is actually supplied by the engine manufacturer, so Mercedes. So we're a Mercedes engine team. One of the things we don't do is engines, and the rules stipulate that. The difference, we all buy off-the-shelf cells from the normal big cell suppliers. The difference will be in how they're packaged, cooled, and most importantly, probably the control of those as well, the battery management system that sits over the top. And that's one of our sort of key areas to take out into other markets, and one of our differentiators is the battery control system and battery management system that sits above the actual physical cells. Anyone else? Good stuff. Well, I'll be outside in the speaker's corner if anyone wants to ask me any more questions. Happily talk about anything else you'd like to ask. So thank you very much.